Hi everyone. You're looking at two shaded pole motors that were cut down, and what I'm doing with these basically the core and coil of these shaded pole motors. By the way, shaded pole motors are found in like a bathroom fan, a cheap bathroom fan. Actually, these came out of that, and you can find them in microwave oven as well. They have just like a little fan that circulates the air. Anyways, got these for like $20 each, the motors. Just got it out from the fan and cut them with a very fine, it's called a cut-off blade from an angle grinder. But you have to keep all these laminations under compression, so they're in a vise, and you have to make sure that they don't expand when you're cutting them, and you have to take a lot of time and a lot of care. If not, you're going to just ruin these things. So anyways, what I am testing here is the Flynn parallel path, I guess, setup. And I've got obviously one coil here, one coil there, and here the magnets on this coil here are both on the north poles here on each side, and the magnets are on this side obviously in the south pole. And what this this Flynn parallel path gives you is a permanent magnet flux switch operation. So you can turn on and off the flux of a permanent magnet, okay, utilizing this system. So let me explain a bit how this system works. Right now I have a microwave oven transformer here, and I'm using that as a really heavy weight. That's a huge transformer. It's probably one of the biggest microwave oven transformers that are on the market. Forget that plug there, that has nothing to do with anything here. So I'm just using that as a weight, and I'm going to lift that up in the air. So you see these neomagnets here, which are 1/2-inch round neomagnets, and I've got 5 of them all together here. Okay, and those magnets are holding the whole weight of this here. I don't know how heavy that transformer is, but it's over 5 pounds, I'm sure. Now what we have here on this side here, we've got a north, right, on this one, and a south here. So we've got a magnet happening, you know, a natural magnet happening in here, so it's got a lot of good pulling force. We're utilizing both poles of the magnet here. So it's kind of bridged here. So what happens is these coils are there so that once they are energized, what's going to happen is the flux switch will actually let go of any pulling power here, meaning the natural permanent magnet here, the flux will cancel itself here. But actually on this side here, it actually becomes over 3 times stronger. So if there's a piece of metal on this side, it's going to go donk, and on this side it's going to let go. Okay, so we're going to have this full over 5-pound weight here pulled up in the air, and I'm going to apply a small voltage, and you'll see it capable of letting go, and we'll calculate the amount of energy, and it's very surprising how little energy this is taking. So I bought these because it's a lot easier than, you know, winding coils and, you know, getting laminations and stuff like that, and I just wanted to get a little bit of tests done before I invest more time into this, and it seems to be giving a good result. So what I have here is a little pulse circuit that I've made in the past for testing coils, and you might recognize it from another video. So I've got a little micro relay here that is a capacitive discharge, okay, working on a capacitive discharge going to this more heavy-duty relay here, which is a 24-volt relay. So 24 volt is getting discharge from about 11 microfarads here into this relay, so that it creates a very short pulse. So it discharges this capacitor here, which is a huge capacitor, by the way, but it's not going to discharge that whole capacitor. 30,000 microfarad rated at 30 volts, but I'm going to be charging it higher. I'm going to be charging it at 37 volts, okay? And we're going to discharge it once it is stable at 37 volts, and we have a little battery here that we can discharge it just by doing one click here, and we've got a discharge happening. So I'm also collecting the flyback, but this is very efficient and there's hardly any flyback energy coming back. Very, very minimal, hardly worth talking about. And but I'm doing that anyways just to keep the contacts clean when you collect the flyback. It makes less of a spark and all that. So at the back here I've got 3 batteries in series, and I'll be charging that capacitor, this one here, up to 37 volts. And I've got another tap point here, 24 volts for the voltage required for my 24 volt relay here. So that's about it. And the reason I'm using this large capacitor is there's a reason, and it's very interesting, interesting effect, and I'm going to share that with you, and you'll see that it's I don't understand it, why it's doing it, but anyways, I'll show you what it's doing. First of all, we'll do a test now to see if we can, you know, how much energy it takes to let go of this huge weight here. So hang on, I'll put the camera on the tripod. Okay, we're back. Okay, we're back. So now I'm going to lift it up. We are airborne, and we're going to wait till we have exactly 37 volts on the voltage meter right there, and we can hit the switch right now. Okay, so if you observe the voltage at 36.8, all right, or 8, actually 8, it was 8.5. So that capacitor is losing its voltage because I'm actually overcharging it, okay? And that's the interesting thing that I've noticed. What I'll do right now is we'll give it one more shot. I'll recharge it. To 37. And we'll do it one more time. And I'll wait for my signal. And now. So you see it's at 36.9. So we're actually using, like, you know, millivolts here on the capacitor. So we'll look at the calculations. Okay, so here are the calculations. 37 volts at 30,000 microfarad gives us a total of 20 millijoules. 20 joules, 20.535. And here is the next calculation. 36.9 volts was the remaining voltage in the capacitor at 30,000 microfarad. And that's 20 joules, 0.424. So we've utilized about 100 millijoules. So here, just to finalize, is another shot of the setup, or the device if you want. And these magnets are, like I said, 1/2 inch diameter by 1/8 thick, and there's 5 of them. But you could probably just use cubes. I just don't have 1/2 inch cubes. And these are the connections here for the cables here. So basically one is reversed to the other, each coil. And you know, I just use these receptacles that were on the fan itself to just keep it simple and handy to connect and disconnect. You can just flip it around to get the polarities right on the coils. And the interesting thing I find is this: if I'm using a high microfarad value capacitor, and if you can charge it up to beyond its normal operating voltage, I find they are more efficient. I found this before, as far as utilizing very small amount of energy from it, like I did now, using about 100 to 110 millijoules is nothing if you calculate how much it has to overcome, you know, this flux. And it did that, and obviously you saw it let go to that microwave oven transformer easily. And I'll do a weight check on that and post that information in the topic as well. So thanks for your interest, and talk to you later. Bye now.